Now we will see the application of your Biot-Savart's law. So that are mainly due to the straight wire. What is the magnetic field? That is due to the straight wire. Then again due to the circular arc, then circular loop, and because of your solenoid. So before that, one more thing that we can see. So we can compare that Biot-Savart's law along with your Coulomb's law also. Yeah, so if you remember that, so definitely the Coulomb's law, it was only due to the point charge, that the point charge is the source for your that electric field. So definitely this charge Q, that source is nothing but it is only a scalar quantity. But on other side, if I consider this current carrying conductor which is producing that magnetic field, obviously it is a vector quantity. So that is one of the important difference between that. You can say the field, that is electric field and magnetic field, and along with the source which produces it. So now the magnetic field due to the current carrying, first we will see because of this straight wire. So this is the formula which I have written over here. So again you can say that, so let's say this is a wire which is nothing but finite wire. So definitely this is a finite wire and which is going to produce, so let's say these are the two ends A and B for this finite wire, and this is the point P where you have to find the magnetic field. So the first thing you can do is find the perpendicular distance from this point P onto this line. Let's say it is nothing but the R. Then join this extreme ends over here. Then you will find that it is making some angle. The first one, it is making the angle of phi 1, and the second one, it is making the angle of your phi 2. And this is how you can show the direction for that current. So this magnetic field, again you can find by just selecting one of the triangle over here. So let's say this is phi 1 we have just written. So again you can say, let's say this is the angle theta. Again just consider this is the element dl. Yeah, by just doing this process, finally we will get this result of your mu 0 I upon 4 pi r in bracket, that is a sine phi 1 and sine phi 2. So obviously we just said that this phi 1 and phi 2, these are the angles which are just, that is extended by this your extreme ends at the center of this your line which joins to the conductor. So these are the angles phi 1 and phi 2. So this is a very important expression for this, the magnetic field because of your finite current carrying conductor. So in this case, again there are various cases. So if I assume that now this conductor is infinite, if I assume that this conductor is infinite, so then what is the value of this phi 1 and phi 2? So if it is infinite, so definitely you can say that this angle, so if it is a infinite, so that means you can say that this angle goes on increasing and increasing. So you can say that likewise if it goes on increasing, so finally it becomes phi is equals to, or you can say that this phi 1 is equals to phi 2 which is equals to 90 degree. So that angle becomes 90 degree. So then you can write it down, this B is equals to, that is mu 0 I upon 4 pi r, then that is a sine 90 plus sine 90, so which is 2, 1 plus 1. So then you can write it down, that is a mu 0 I upon 2 pi r. So this is the expression because of your infinite current carrying conductor, the magnetic field because of that infinite current carrying conductor. You can say that it is mu 0 I upon your 2 pi r. So this is one of the very important case. One more case that we can consider. So let's say this is infinite carrying conductor and one of the end. So you have to find the magnetic field at point P. So in this case, obviously the conductor is infinity. So one angle, that phi 1 will become 0 and your phi 2 is nothing but 90 degree. So this is also one of the important case, so where you can just put the values for that and you will get the resultant expression for that magnetic field. when the point of interest is at one of the end, and obviously this perpendicular distance is r, so you have to join these extreme ends. So obviously when you join it, you will get the value of your phi 1. Obviously phi 1 and r both lies on the same axis, so that's why the phi 1 you are getting as a 0 degree, and phi 2 you are getting it as a 90 degree. So the same case again at either end also you can do the same thing. So if it is point P at this location, you can say now phi 2 is equals to 0 and phi 1 is equals to 90. So likewise you will get this case, or this is the in general expression for your magnetic field due to the finite current carrying conductor. Similarly, now we have to find the magnetic field due to the current carrying circular arc. So now this circular arc, so let's say this is the circular arc and through which the current I is flowing. So again the procedure is simple. So let's say you have to find the magnetic field at point C. So consider a small part of that circular arc. So let's say this arc is having the length dl, then join the center of this arc dl to the center C. Obviously this again makes the angle of 90 degree. So now what is the magnetic field due to that small element dl? So which I can write it down that dB is equals to, that is a mu 0 upon 4 pi, again ideal sine theta upon r square. But now here we can see that the value of your theta is equals to 90 degree. So then definitely your dB becomes your mu 0 upon 4 pi. Then this is your ideal upon r square. So now again this dl. So then how you can just write it down that dl? So basically this value of b is now the integration of your dB, again which is your integration of your mu 0 upon 4 pi, your ideal upon r square. So this mu 0 upon 4 pi r square is a constant. Again this I is also constant, and this is integration of dl. So obviously integration of dl is L, and again further I can write it down, if this entire length is L and this radius is r, so let's say this is nothing but the theta. So we know that your theta is equals to L upon r. So that means definitely I can write it down, L is equals to r into theta, and further I can simplify. So this is mu 0 I. Now instead of L, this is r theta, and again 4 pi r square. So further I can say that, so one of that your r will get cancelled, and I can say that this is mu 0 I, then again this is theta again, then I can say that this is a 4 pi r. So this is the magnetic field due to the arc. So that is your expression in general for the magnetic field due to the arc at the center.